Welcome everyone to the third PhD talk of OBERON. Happy Easter for all of you. I hope all of you are fine in your life and in your research. Today we are here to listen to attractive talk of María Mechó García, the PhD researcher of University of Minho, who is working on the wavefront aberration during accommodation, and also to build a statistical model of these changes. A bit about his background, I need to say that she's graduated in the field of optic and optometry from the University of Valencia. And she continued her studies in optometry and science vision in that university. Sorry, I forgot to tell something. I should say that welcome, Said, to the OBERON project. We all wish you will be successful in these studies. Okay, so thank you so much, everyone. Maria, we are here and we are interested in your attractive talk about visuals optic. Thank you.
Can you hear me?
Yes, yes.
Okay. And are you seeing the presentation now?
Yes, we are. Yes, we can see.
Okay. 1 second. Okay. So, good morning, everyone. Today is the third student talk, and we are going to talk about the visual optics. First of all, I am going to introduce the visual process that is composed by 3 parts: the optical state, the retinal state, and the cortical state. Firstly, the optical state. As we know, the eye is an optical system that is composed by 2 principal refractive elements that are the cornea and the crystalline lens, and then one element where it's projected the image, that is the retina. So the cornea is the most powerful refractive surface of the eye, and it's a curved surface, transparent, and it's covered by a LCR film that maintains the optical quality of this cornea and the refraction. Then this surface is followed by an anterior chamber that is filled with a liquid that is called aqueous humor, and it's transparent liquid. Then after that, we found the iris that allows to contract and dilate, and have in the middle a hole that is called the pupil. This pupil dilates or contracts in response to external illumination, and control the amount of light entering into the eye. So this amount of light will affect the quality of the retinal image into the eye, influencing some we have the crystalline lens. This crystalline lens have the ability to change the power as we change the focus distance of where we are seeing. For example, if we are seeing in the near vision, this power
Yes, I think, Maria, we cannot hear you. I think there is some problem in connection.
The eyes that we know. And after that, we have the retina. The retina is the part where the images are projected. from this refractive surface. Well, the eye, the normal eye, the emmetrope eye in a young adult, it's more or less 24 millimeters and have 16 diopters of refractive power. But the main refractive contribution is the cornea that have more or less 42 diopters, and the crystal lens that have will increase as I explained before. Then we pass to the retinal state. The retinal is the neural structure that is located in the fundus of the eye and is light sensitive. So this tissue is directly connected to the brain through the optical nerve, which is involved in the signal transduction of the information and the conversion of the light into the neural signal. Typically, retina, the position of the retina in an accommodated state and the relation of the focus image projected by the cornea and the
sorry, Maria, I am interrupting you. Can you hear me?
Yes.
I think there is some problem in connection because people cannot hear you. Sometimes it is not stable.
Really? Okay. Let me see. Okay. Because I'm with internet, but I don't know. I don't know how to solve this.
Okay. Okay.
I think maybe you can switch off your camera so that your connection is more stable now.
Okay, so I will turn off the camera just in the presentation and then I will turn it on.
Okay, thank you.
Okay. And if you are not hearing me, tell me another time. Okay, so I will repeat it. But do you want to repeat anything?
No, but I mean sometimes it was disconnected. You can continue. Yeah.
I'm going to start with that slide also. Okay. So are you seeing now the slide?
Now I cannot
see. The presentation?
See. No, I cannot see.
Okay. Sorry. Okay. I think now.
Yes, now it is okay.
Okay. Thank you. Okay. So I'm going to start with that part another time. So what we are in the retinal state. So the retina is a neural structure that is located in the eye fundus, and this part is a light sensitive tissue. This part is connected to the brain through the optical nerve, and it's involved in the signal transduction of the information and the conversion of the light into neural signals. Optically, the retina is and the position of the retina in the unaccommodated eye and the relation between the focus image projected by the cornea and the lens determines the refractive states of the eye. For example, here, if the retina, if the light focusing to the retina, we will have an emmetrope. If the light focus in front of the retina, we will have a myope, that it's a refractive state that we will correct it with negative lenses, and here an hyperope, that the light focus behind the retina, and this refractive state will be corrected by positive lenses. Also, we have a refractive state called astigmatism, where the light focus in different parts of the retina. Histologically, Histologically, the retina is composed by several layers, and these layers are in total of 11 layers, and the light comes from this point of the eye and goes to the first layer of the retina, that is the inner limiting membrane. This layer is called, that is the more interlayer of the retina, and the last layer is the membrane, the branch membrane. So the light travels through all the layers until reach the photoreceptors. The photoreceptors are the cells that are sensible to the light. So these cells are the ones that takes the light and transform the signal into neural signal, and then travel in the other way to the optic nerve. The optic nerve is where the information is going to travel until the brain. So now I'm going to explain with these photoreceptors, because we have different types of these photoreceptors. Firstly, we have the cones and the rods. The cones are the ones that are low level light sensible, and the cones are the ones that are sensible to a specific wavelength. Of these cones, we have three types. The ones that are sensible to the long wavelength, that are the red ones, the ones that are sensible to green wavelengths, and the ones that are sensible to small wavelengths. Each one has a peak of expression. So these photoreceptors are not distributed in the same way in all the retina. We have the distribution. It's depending on the high resolution points in the retina. We have a high resolution point in the retina that is called the fovea, and it's 1.5 millimeters of wide, and it's this point. Here in the eye, you can see that it's near the optic nerve, that is here. And here we have just photoreceptors, but cones, just cones. In the peripheral parts of the retina, we will have more rods than cones. Here there is a map with the distribution of this type of photoreceptors, and in dashed lines we have the cones, and in normal lines are the rods. Then here there is a blind spot that it's where the optic nerve is located, because in that part there are not cells photosensible to the light. So this part is more or less 15 or 20 degrees of the fovea, and it's located in the nasal part of the eyes, both eyes. Now I'm going to explain the limitations that we have in the retina.
I lost her.
I think she's disconnected again.
Can you see?
Yes, we can see, but sometimes we cannot hear you. Now it is okay. You can continue.
Okay, thank you. So we have the Stiles-Crawford effect, and it's an effect. It's an effect that takes into account the directionality of the human cones and how the light impacts in these photoreceptors. Saying that if we have if the light impacts in the center part of the pupil, the cones will have more response than the ones that the light that enters in the peripheral parts of the pupil. So these photoreceptors from the peripheral part will have less activated. So this is the style Stratford effect. Then we have the mosaic of photoreceptors that is that if we projected an image into the retina and this image just is sampled by a single cone, this cone have not the capacity to differentiate the components of each object. For example, here an. So we will have no response about this object, this signal. But if the E impact in more than one cone, the photoreceptors have the capacity to resolve what we are seeing, and we have this information, and we can process it in the brain. And after that, we have the Nyquist limit that it's estimated around 60 cycles per degree and has to be with the minimum reasonable acuity. So when the spatial frequency of a retinal image is about this Nyquist limit, and under sampling occurs, and there is a misrepresentation of the signal. So there is no projected, yes, there is projected into the retina, but not signal, and we call this effect aliasing. And after that, the cortical state, where the neural input that leaves the retina goes via the optic nerve and travels until the chiasma optics. Here we differentiate two types of retinas, the temporal one and the nasal one. The temporal one always travels in the same path, but the nasal one cross over and in the chiasma optics and goes to the other part of the brain. So here we can see that the right visual field is processed in the left part of the primary visual cortex in the area B1, and the left visual field is projected in the right part of the primary visual cortex. Is associated with the limited aperture of sight and predominant in small pupils. And what happens with this effect? Here we can see that the light source goes linearly and
Maria, we are losing you. Can you hear me? Okay, I think she's disconnected.
we don't have just one light of source. If we have
Maria,
more
we couldn't hear you for a while. I think maybe it is better to explain.
We have an effect with sorry.
Can you hear me? Can you hear me now, Maria?
Bajura. Can I continue?
I think you should continue this page at first because I think we couldn't hear you.
Sorry, Maria, do you have the possibility to change your room and try another connection, or it's the only connection possible?
No, está. ¿Sí? ¿Estás a oír? Okay. Sorry.
No, we are waiting for you, but I think it is better to be in a place that is a little more stable.
Yes, I don't know why here is not stable. I mean, I did more presentations here, but I'm going to go to the other.
Yeah, okay,
room.
don't worry. Just don't worry. We are waiting for you.
Okay. Thank you. Sí, ya hacen. Disculpa. Okay. I'm going to share the screen another time.
Okay, thank you.
Okay. Did you hear this part?
No, I think you should explain this page at first.
Okay. So here what I want to explain now is the limited effects that cause less optical quality in the eye. So I'm going to explain 3 of them. The first one is the diffraction. The diffraction is an optical factor that is determined by the pupil size. And what happens in this effect, you can see here, there is a monochromatic source that enters an impact in an aperture, and these apertures have what did it to change the trajectory of the waves, and when impact in an screen here, but in the eye will be the retina, the intensity of that wave have this distribution with a central maxima and then other less maximas in the periphery. This effect is called ID disk, and it seems like that. But what happens if we have more than one of light sources, that we have the problem to distinguish 2 points of that, because here we have more disruption, so we are not able to distinguish 2 or resolve 2 points. So there is a criterion that is called the Rayleigh criterion, and it says which is the minimum distance between the two central maxima that have to have the light sources to can resolve these 2 points. Then the other effect is the scattering. The scattering is a physical phenomenon that is inherent to the light propagation to the media, and they have to be with the optical inhomogeneities of the eye. So what happens is the light source comes in that way, and if there is particles in the media, the light impact in that particles, and that particles produce a change in the trajectory of the light. So we have different parts in the eye that scatter. For example, the cornea, the crystalline lens, and also the retina have properties that scatter the light. But also, I want to share with you that some diseases in the eye produce scattering, as the cataract, that is opacity in this lens, in the crystal lens, and produce this image. This is a simulation, but more or less will be that like that. And also, if the cornea have scars as are in the keratoconus or other disease in the cornea, and refractive surgery also produce this effect. And the last one is the aberration. The aberration is represented by the difference between a perfect spherical reference wavefront and an aberrate wavefront, and the distance between these both, it's what we call the aberration of the eye. It's depending of the pupil size, so as higher the pupil, higher aberrations we will have in the eyes. Here we have some simulations. Here is a map of elevation of a perfect eye. What we see here is the object, how it's impact in the retina, and how is the image of this object. And here, if we do this refractive error of an eye, if we simulate this vision, we will have this object and how it's in the retina, this image. So now I'm going to explain that the aberration have 2 types. This part was explained so good by Iñaki, but I want just to remind that the low order aberrations are the ones until the 2nd order in the Wernicke polynomial pyramid, and these aberrations have the focus and the astigmatism. Also, the high order aberrations are the ones that have less contribution in the optical quality of the eye, but in some disease it's really important to take into account these high order aberrations. Also, I want to say that the low order are the ones that are corrected by contact lenses or ophthalmic lenses, but the higher order are not able to be correct with that corrections. Then the chromatic aberrations that are depending on the wavelength and how they impact into they are focused into the eye. Here are represented an image of eyes where the medium wavelength is focused into the retina, the small is focused in before the retina, and the large ones are focused behind the retina. And there are two types of chromatic aberrations: the longitudinal lattice, where that are focused in the axis, in the optical axis, and the transverse chromatic aberration that are focused when the object point came from the off-axis. And now I'm going to explain the optical quality metrics. There are two types of optical quality metrics. One calculated by the pupil plane, and the other calculated by the image planes. By the pupil plane, we have the minimum root square that have into account the Zernike polynomials of a low order, and the paraxial curvature matching that have into account the Zernike polynomials of higher orders, as the spherical aberration of primary spherical aberration and secondary spherical aberration. And then the image plane metrics that are some of them and one to each other are related. And first of all, I want to explain the point spread function, that it's how an image of a point object through an optical system is seen. So to calculate the PCF, we have to calculate first the pupil function, that is have the apodization function and the aberrated the wavefront aberration of the eye. When we have the pupil function, we can do the Fourier transform of this pupil function, and with k that it's a constant and the axial length, we can calculate the PCF. The PCF is represented here of a same subject, how the PCF changes with different pupil size. And here we can see how we can read see how an image object is projected into the retina, calculating by the calculation of the PCF. What we do is to calculate the wavefront of this eye, the aberrations of this eye, multiplied by the pupil function, and then with that calculation, we do the Fourier transform, and we obtain the PCF. And the PCF, the convolution of the PCF in the object, we will obtain the image object. So we will obtain how this object is seen in the retinal plane. The optical transfer function, it gives us the information about the loss of contrast in the retina as an effect of sinusoidal target, and is calculated by the transfer function, the Fourier transform of the PCF. The modulation transfer function, it represents a decrease in the contrast as a function of spatial frequency, and can be calculated as the modulation of the OTS. And here we can see how an aberration-free image, calculating the point spread function of this, we obtain that the maxima will be at 1, so the modulation transfer function will be perfect. But here, if the point spread function have a low peak intensity at 0.4, for example, we will see that the modulation transfer function is behind the perfect modulation transfer function calculated before. And then the Strel ratio, that it's an scalar metric that describes as the quality of the PCF and can be calculated by the spatial, but can be calculated in two types, spatially and frequency. With frequency, spatially with the PCF, and frequency with the NTF. And the visual strain is the volume under the CSF, and is calculated by the neural CSF and the optical transfer function. And here you can see it's a simulation where the wavefront change. I'm going to play it now. The wavefront will be changing, and we ask this wavefront change, the PCF, retinal PCF will change, and also the MTF, and we can see how in the retinal image change. So I'm going to play it. It's quite short, but you can see. I'm going to play it another time just to. Okay. Want this, I can send you also. But the last part, I want to explain the accommodation because it's one of my fields now. So it's a brief introduction about the accommodation, but just to let you know that the accommodation is the ability to the crystalline lens to change its shape and the contribution of the optical power of the eye. So we can see here how the accommodation, how the surface change when the accommodation is stimulated. As we can see here, the anterior chamber depth decrease, the lens is more flattened, and we have more relaxation in the zonal zone, and also the pupil size decrease. Here in the right side, I want to share with you the ideal accommodative response that will be 1-to-1, but this is not what happens in the real eye. In real eyes, young adults or adults less than 40 years, because more than 40 years will be this will be decreasing because the presbyopia starts to appear, and it's a disease where this lens don't work. So this effect is just happens in young or young adults, and in red you can see which is the real response of a subject about the accommodative demand, where we have a lead here in the initial state that it's advanced in the accommodation, and then in the 2 diopters of accommodative demand turns to the lag that we called lag, but it's a delay on the accommodative response. And now I'm going to explain some cues or factors related to the optical quality of the image projecting to the retina, and that have implicated in the accommodative control, as the blur that is considered the primary stimulus of accommodation. Then we have the chromatic aberration, because as we can see here in the images, if there is over-accommodated or under-accommodated, the eye produces different images. So these different images will give us the stimulus to accommodate. Also the high order aberrations, because also here there is an over-accommodating and under-accommodating eye, and the images that are produced. This is a simulation, but the image that produce, it's different one between the other. So this gives us some cues to respond to the accommodative stimulus, and also the fluctuation of the accommodation that could play an active role in controlling the accommodation. And I hope you understand all with this
Okay,
problem.
thank you. No, thank you so much. It was good. Of course, we had a lot of problem with connection of internet, but it was good. Thank you so much. If anyone has any question, you can ask. Benedetta?
Okay, can you hear me?
Yes.
Yes.
Okay, thank you, Maria, for your presentation. Connection problems can happen, but we understood everything, so thank you a lot.
Okay.
And I just have more of a curiosity. I don't know if it's related, but I was wondering, when someone is affected by the astigmatic defect, usually, especially during night vision, I think the person perceives like when lights with like shape, linear shape. I don't know if I'm being clear, but why this phenomenon happen?
Because this disease happens because the cornea is not as a sphere, it's more like a rugby ball, okay?
Yeah.
Just to perceive. So one radius is more one focal. Well, one meridian has less radius than the other. So the light focus in different parts of the eye. So, for example, if one focus is in behind the retina and the other is in front the retina, this produce this image.
Okay,
but
so this
also
is the effect. I mean, because I notice with myself, this happened to myself, for example, that especially when I'm driving during night, when I look at lights, like it bothers me a bit because I see these like these defects. I don't know how to explain them.
It's normal, and also because during the night you have a large pupil size, so the effects of these factors increase the effects. It's not like during the day. During the day, this could be corrected by your brain, but during the night, it's more difficult.
Okay, thank you a lot.
Okay, thank you, Benedetta. We are waiting for another question. Okay, maybe everyone understood.
No questions.
All of no question. But I have a small question, very basic. I mean, it is very basic. I mean, we have cornea and lens as an optical system, okay? And the aberration is happening in both of them, right? I want to know that finally the lens is responsible for control that aberration. Is it correct?
What? So, I mean, the aberrations are, depending what aberrations you are measuring, because the ones that I was explaining today was the ocular ones, the total ones. But the aberrations in the crystalline lens remain in the same magnitude if you are not accommodating. Okay, so when you stimulate the accommodation, here there is a change in the aberration. There is a change in the higher thermics that I explained with this parameter.
Yes.
Here change the aberration. But what you are saying is to remove the crystalline lens to measure the aberrations here.
No. I am telling because aberration is always influence on the quality of image.
Yes, always.
I want to know that the lens is finally responsible to control a lot of aberration to
Yes.
produce. Yeah, this is correct.
The last slide that I present are some of the cues that have the accommodative system to correct these aberrations, to improve the quality of our vision.
Mm-hmm. Okay, thank you. Thanks a lot. Okay, I think
Laura, maybe
yes.
Said want to introduce himself, no? We can ask him.
Yes.
Yes.
Okay, Said, if you want to introduce yourself, we are here and we want to know you. Welcome.
Thank you so much. Can you hear me?
Yes.
Hi, everyone. My name is Said Zahabi. I'm from Iran. I lived in Isfahan. I completed a master's degree in mechanical engineering from Isfahan University of Technology about 5 years ago. And right now I'm a researcher in OBERON project. It's my pleasure to invite you to this online meeting. And I know that all of you, all faculties, researchers, postdocs, and PhD students are capable and notable in your own field. It's a good opportunity for me to learn more and boost my skills to do anything that we need in the OBERON project. And I like to mention that my supervisor is Dr. Magdalena Asechik, and my advisor is Dr. Milad Salemi. Thank them to consider me for this position. And I try to do my best to satisfy them and execute anything I know to achieve desirable outcome at the end of the project. Thank you to having me.
Thank you so much. Welcome to our group, and we hope we have a very good research with together, all of us.
Thank you so much. Yeah, I hope that.
Okay, I think we should finish this meeting, but I should say that the next presentation